we have successfully assembled or compiled a binary file. What does that mean? Oh, well, let's have a look at our binary file. Why don't we? There it is, but you can't just double click and open it in most cases. Sometimes you can, depends. You'll probably get an error. Okay. Like I said, the power of KAOS runs from the command line here. So we have a secret weapon for that called Ghex. There you go. And again, we're already in the same folder, good to go. So we're just going to specify what file we want to look at, which is o1.bin. Okay, boom, there. So we are now looking at our first binary file. And like I said, it turns everything we write into ones and zeros. Well, we have stuck a 1 in there, and basically we got 01 in binary. Or technically, it is actually 0000001. You see? And then we have it in every other language known to the programming world. They all look the same, but later these numbers will become complexly different. So there you go. Now, very interesting here. This is the value 1 stored in your computer in binary, right? That could mean a lot of different things to the computer. Now, the computer only thinks in like ones and zeros, okay? So here, if I click on this 1 and type a 2 now, there, I get the same value over here in binary. And you're like, what? Wait, that's 10. No, binary, okay, well, see, that's a whole nother story here, right? And again, this is, I see people ask questions on the internet or whatever. Okay, how does a computer actually convert, like, work on ones and zeros? I don't get it, you know. And they go, okay, for that you have to go learn binary math, you know, which totally has absolutely nothing to do with the case, and or like, you know, or just like totally point you in obscure directions, and nobody ever seems to be able to really, like, seems to answer the question, which seems simple enough, you know, how does this communicate with the computer? Well, let's explore a little bit over here, okay? Here's what we know about binary. Let me go back to 1, you know, here, or even 0. There, 0. Let's just think of this in just terms of just this 1 digit for now. You know, imagine we had a 1-bit computer. You could think of the light switch on your wall as being like a binary 1-bit computer. All it can do is one thing. It can be either on or it can be off. 0 in this case representing the off state, and 1 representing the on state, right? So in that value, all I can possibly contain is a value of off or on, or 0 or 1, right? That's all that thing can ever do, right? Now, if I combine, go to a 2-bit system, of course that's only worth a quarter, so we're not going to concern ourselves with that. No, a 2-bit system would mean I could go from 0, 1, or if I wanted to do 2, you know, I can say this is our 2 field, basically, and only working in ones and zeros, you know, I'm going to say this can now be a 1, right, and this will be a 0. Okay, so now, hang on here. I'm sorry. Oh, value of this. I got a different thing down here. No. That's another issue. I'm getting ahead of myself. Put a 2 in here. There. This is a value of 2, right? Equates to the number 1 and 0. Right? This being the, now gives us 4 possibilities, right? The first possibility being 0, 0, right? The second possibility being 0, 1, right? The third possibility being that this, let me just make this a 2 now, that this is 0, that this is 1, and this is 0, and the third possibility being that both of them are 1, see? So that's as high as our 2-bit computer can count. It can count to a value of 4. Why does this say 3? Well, because 0 is also we just counted 4 possible places. 0, 1, 2, 3, right? Which gives us a total of 4 possibilities, okay? So that's as high as we can count now in a 2-bit operating system. How high can we count in a 3-bit operating system? Well, it breaks down to like this, okay? 1 we know is 1, okay? This is all in binary. It's either 1 or on or off, places of 2, right? So this will be 2 times 1. Anything in here is 2 times 1. Anything in this place will be 2 times 2, or 2 to the second power, right? Anything in this place will be 2 times 2 times 2, or 2 to the third power. Anything here will be 2 times 2 times 2 times 2, or 2 to the fourth power, etc., etc., etc. Okay, so what it boils down to is that each one of these is double the previous one. The value that's stored in here is worth 2. The value that is stored in here is worth 4. The value that is stored in the next one is worth 8, 16, 32, 64, 128. So there's a maximum of between 0 and 127 possible numbers that we can store in an 8-bit value, okay? 8-bit being known as a byte, right? This is basically like the minimum number of characters that you would need a byte to store a single letter, right? Actually 7, 6 would be the minimum you can store letters. If you want periods and other things, exclamation point, a couple other things, you can get away with 7. 8-bit, now you can also, have slash and 1, 2, 3, 4 up and down, and a lot of throwing some other things in there. Okay, so 8-bit gives you that many possibilities. 127 possibilities, which we only need 24 letters in the alphabet, you see, so that gives us enough letters, plus 9 digits from 10 from 0 to 1, okay, 34, so it gives us a bit to spare. Nice, that can be stored in 8 bits of memory. Okay, there we go. So now that we've just viewed our first binary file, let me bring this up a little bit now. I'm going to bring this value. I'm going to close this. Don't save. I made some changes. You can actually edit here in Ghex and save it out from there, right? For the time being, we are just going to be working from our assembly file over here. Okay. So what happens if I put like a value of 10 in there? Okay, I'm just going to save my file. Head on over here to Linux. Another nice feature of Linux, I can just hit the up arrow and it will remember the last command that I put in there. Very nice. If I hit the up arrow again, oh, the command before that, and etc., etc., etc. Okay, there's my compile command, already still in Linux command line memory. I'm going to just compile my program again, and then go. Last command was I just compiled it again, but if I go the one before that now, I Ghexed and I look at the value of 10 and I get 0A. And, okay, now what's up with that? Okay, now we're going into the land of hexadecimal. See, because the highest value I can show you here is the value of 9, right? And then the problem is we're not dealing in a decimal, something that can give you 10 places. You know, we're dealing in binary, which can give you two places. So a convenient way of kind of breaking that down is to convert to hexadecimal here, hexadecimal, which is 16 places. That works out very nicely because 16, 2, 4, 8, 16, 16 bits, works out very conveniently, where I can now focus on the leading bit of a number here in hexadecimal. So since I can only represent the values of from 0 to 9 in digits, now in hex we go off into this land of also needing to represent 5 other digits, in which we can just assign as A. See, I get the value 10, you see, B, 11, C, 12, D, 13, E, 14, F, what happens if I put a G in there? It doesn't go that high. See, F is as high as it goes. That's 16 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. You see, and why hexadecimal? Like I said, because it's convenient to think in groups of bytes, just for programmers, rather than like having to look at this in ones and zeros. I can think of it more in groupings of 8-bit hexadecimal values or whatever, you see. Okay, so here, F, once it passes F, value of 15, right, then this 16, boom, see, now it goes to the ones place here. Okay, same here. Now I'll go all the way up to 1, 2, 3, 4, 5, 6, 7, 8, 9, F, 31, right? The highest value here. Okay. So then what happens when I go 1 F? I'm going to go back to 0 here, and 2 here. 2.0 is 32 bits, or 32 places in our possibilities of from 0 to 127. Okay, I'll just keep going up here, and boom, exclamation point. 21, 22, quote, 23, 24. Okay, wow, this is starting to resemble my keyboard now. Oh wow, I accidentally put a higher number there. Let me go back to 25%, 26, 27. Okay, I'm going to go here to 30. There's the number 7. Okay, here, I'm going to go back to 32, 31, 30, number 0. Okay, so, now this is a very, very interesting point about computing. Okay, here's the value, the number 1, right? Why is the number 1 begin at, it's not 31, that's 31 in hexadecimal. Why does the number 1 start at 49 instead of at 1, right? Well, okay, it's very simple, folks, because all a computer can understand is a bunch of numbers, right? And that's the only values I can pass to it, as a bunch of ones and zeros. Okay, so maybe the first question that might pop into a logical thinker's mind is, okay, well then, if all I can tell the computer is a bunch of ones and zeros, how does it know the difference between like the number 1, 0001, and a command? Like, I want to tell the computer to do something, right? Well, it's very simple. See, there's a bunch of reserved values in there that will tell the computer to do something else, such as add a carriage return, or end of a line, or these are direct commands to the processor, right? So, and the actual number system, comes in later, in the whole scheme of things, right? Let me even show you something even funnier here. Let me get up to, say, 71. Here, I'm at the letter Q. Okay, 72, 73, R, S, T. See, I'm not in the small letters. You know, it goes from 0 to 01, then it gives me all the capital letters, and it gives me all the lowercase letters, right? I'm going to go 4. Let me go 9. There's Y. Okay, so then we know Z would be A, and then after the A comes the B, you know, and the C, D, E, F. You know, see, there's various other things after the letters in the alphabet, right? So let's just go up to the next value in hexadecimal, which would be 0, 8. There's a period. Okay. 0, 1. What? Negative 127. Wait a minute. Back up a second here. Right. 80. Okay. 79. Here we go. Watch these numbers here. Okay. This is the actual value in decimal that we're used to, right? A value of 112 in hexadecimal, right? If you're following my explanation so far. Now I'm going to go 71, right? This goes 113, 72, 114, 73, right? Okay, all the way up to 9. A, all the way up to F. That's as high as that goes, right? 127. You follow? Now let's go one more. 127, 8. So, in other words, one higher than 127 is negative 128. Give me a break. What does that mean? Like, how could that be, right? Like, so, okay, so what I want you to observe over here now, in binary, okay, I'm going to go back here to 127, which was the highest value I can display in hexadecimal over here. We've gone to 0, we've gone 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, as high as we can go in binary, right? If we go one higher, it'll flip over to here, right? Okay, so let's go one higher again and watch what happens. Boom. We just went to a negative number and flipped over to 1 over here. Okay, what does that mean? Well, what it means essentially is, like I said, the computer can only understand ones and zeros. It has no negative 1. No negative 10. There is no negative symbol that I can send to the processor to give it a command. I can only communicate to this computer in ones and zeros. And so in order to tell the computer that a value that I'm trying to send is negative, this leading value here is reserved strictly for that. If this is a 0 here, then this value will be positive or 0, right? If it was all zeros, and that was 0. But if it was 0 here and anything else, we would have a positive value up to 127. You follow? But if this is 1 and anything else, we'll have a negative value from 128 on down. See that? 2. As I go higher here, that number gets closer to 0, right? Okay, and I'm going to talk next in the next bit of video about how your computer actually processes these ones and zeros, right? So that's using Ghex to have a look at our very interesting data byte that we've created. A byte of information, a byte being 8 bits. 1, 2, 3, 4, 5, 6, 7, 8 bits in binary, right? This much would be called a nibble. That's 4 bits. You see, there. This much here, that's a nibble. There. But we're dealing in 8 bits is 1 byte and can be represented by 2 values here that go as high as FF, 1111111, -1. You see, I'll explain that a little bit more, but let's get on with learning more first, shall we?